some applause to JANIS and support him for his future talk. Welcome.
Yeah. So, actually, it didn't happen randomly. The Baltic Ruby was the final push to organize this meetup. So yeah, thanks you for that. So welcome to my talk, Easy Threading with JRuby. Is it? So first of all, about me, I'm JANIS BAIZA from Latvia, developer at EasyBI. I've been with Ruby since 2010. And in the beginning, I used it more like for side projects, but for last no more than 7 years, it's been my main language. One of my development passions is performance tuning, and even my bachelor's and master thesis are performance related. So yeah, I'm deep in it. EasyBI is a data visualization tool, and it's written in Ruby on Rails. But in background, EasyBI uses Pentaho-Mondrian OLAP engine, which is written in Java. And therefore, we use JRuby, as it provides many useful features in Java-related app environment. And besides software, another my passion is green energy and also data analysis. I had the solar panels installed in my house a couple of years back. And to gain more insight how this investment performs and when it will pay back, I did some additional analysis using our analytics tool EasyBI. So you can see there some graphs of it. And I'm happy to discuss more about it in the hallway track. So today I will talk about threading in general, and we'll look at some practical use cases. So about threading, concurrency, and parallelism. So if you look at the execution flow of any single-threaded code, so there are operations that are like CPU memory related, and the ones that are related like to network, to database queries, or disk reads. The first ones are fast ones because like CPU, memory, they are tightly coupled together with the high-speed bandwidth. And the second ones, as we heard already today, they usually are the slow ones and require more time to complete. In a single-threaded flow, so there are times that we need to wait while those slow operations complete. And to increase efficiency and execution speed, we could like divide those operations in multiple threads. So let's see. The same operations, but divided in 3 threads. As JRuby, by default, all execution is performed in one single CPU core. Execution of this code could look following. We start execution. Operation from any of the threads can be chosen as the next one, and one of the threads reaches this slow operation. And we will need to wait till this operation is completed. But meanwhile, other threads can continue their operation till they reach the slow operation. And also they will need to wait some time to get this information back from the network. Now, the first thread received the information and can continue operations, and similar other threads as well can continue their work, and at some point, execution is completed. So we'll mark this line for comparison. And now look at the same code execution flow, but this time JRuby, where we have Java with multiple CPU core support, like see 2 cores here. And threads similarly can continue execution, but this time any thread operation can be executed by any of the CPU cores, but still we'll need to wait for those network operations to be completed. And when those are completed, then threads can continue their work. And in this very simple example, so we can see that the execution in total completed faster than previously. But that's in theory. So let's look at a simple use case that's imaginary, but still based on something that we are doing in our product in background operations, data processing and gathering. And also we'll look how threading could help, or maybe not, to improve performance. So first of all, so there are a lot of data I would like to analyze, and I wanted to download them to my disk so that I don't need bother this API to reach some API limits. And there are like 200 plus pages of data, and I needed to get those stored on my disk. And each request took around like 2 to 5 seconds, and total it took like 11 minutes. So I thought, okay, quite slow. Maybe we can increase speed by using parallel execution. And so I decided to split into 4 threads. And you can see different threads requesting different pages and with different durations. At the end, total time was a bit more than 3 minutes, so almost 4 times faster using 4 parallel threads. So it's quite nice expectation. But that's remember that the slow part here was network. And after downloading this information, files contain just strings of JSON-like structures. So first of all, we would like to get them into like arrays of hashes, not plain strings. So first operation would be to parse those JSONs. And to add a bit more load, I just multiplied by 4 times so that I have now almost 1,000 files of data. So for JSON parse, straight ahead approach. Use those contents, use flat map, and JSON parse. At the end, it took almost 8 seconds and loaded almost 95,000 records. I will create a small table for visualization so we can compare our next steps to the previous. So previously threaded execution worked faster. So let's try how this will work. I split those contents into 4 groups and created a new thread for each group. And it took a bit less, processed the same count of records. So let's compare how much less. Yeah, not maybe as fast as we would expect by our previous experience, but okay. So yeah, it was faster. Now we have array of JSONs. Let's add our imagined processing algorithm. So we would like to count, like for different fields, how many times the field appeared in those records. And this completely walks through our already prepared hashes, so it will be completely memory and CPU related operations. And in total, it took like 0.1 second. So it's okay, but if we would like to compare, and maybe there is overhead to start and etc. So not very useful to get rid of additional stuff. So let's 0.1 second. And so let's just multiply it 100 times. And yeah, now it's 11 seconds, something we could compare in different cases. Also mark in our results table and see how it's doing with the threads. So this time also the same, using this in-group function, and for group create a new thread that will do the same work. And in total, we see that the total and real CPU times doesn't differ so much, so not much of parallel execution. And if we compare it to the previous, it's almost the same result, just like 0.2 seconds difference, and I would say the same. So not much of parallelism. Therefore, let's switch to JRuby. JSON parse, yeah, it's in the single-threaded execution a lot slower, I would say, than in CRuby. But if we look at the parallel execution, then we see that those numbers are much better than previously. Will it be the same with the transform operations? Or maybe there are some new results? And the same, we can see that we got almost 4 times better results also in our transform. So let's add to the table. We can see for the JSON parse, we got 3 times better results. For the transformation, almost 4 times. So yeah, JRuby gave us a boost. So very easy. We achieved what we wanted. So okay, thank you. We get or we didn't get. Maybe someone already could guess what's wrong there. Huh? So I left out intentionally some few lines in my previous slide. And the issue is with the data counts. As you can see, there are differences in those numbers, not as expected, and even with the hash differences. So what? And actually, sometimes I got an error in the line where assignment was done, so that some of threads started to initialize this value but didn't complete, and the next one already tried to write something there. So what caused the issue? Let's look at the code again, and especially this one line where we increment the value. This plus equals operation actually are 2 separated operations. First, we need to read the current value and then write back the new one. And if we recall from previously, thread context switch can occur at any time, so we could read the same value twice. For example, let's say the count is 21. Thread 1 reads value 21, and then context switch is occurring, and thread 2 also reads the same value. Now thread 1 increases and writes back 22, and thread 2 as well increases and writes back the same value. So we did the same operation twice, but increased by only 1. And in JRuby it was very obvious because there is this parallelism. In MRI it also can happen, but you need a much bigger data set. So is there a way to get parallel execution in really, but thread safety? Yeah, we could use mutex. So we initialize mutex, and then for each this operation we would like to be thread safe, we use synchronize, and this will ensure that no one else can execute this code. But what will happen to other threads? So they will need to wait till this one releases lock and they can continue. And let's look at results. So JRuby, well, not so good anymore. And if we add to the table, we can see that it's performed even worse than previously. And that's because we needed to do a lot of context switching, a lot of locking. And this wasn't a useful case this time. But synchronize can be useful, and I will discuss about it a bit later. So what we could do to achieve this our goal to get faster execution by using parallel execution. So in our company we use concurrent Ruby gem when interactions between different threads is needed. What is concurrent Ruby? So that's what's written in their GitHub repository. So modern concurrency tools for Ruby inspired by other programming languages and classic concurrency patterns. And the gem makes one of the strongest thread safety guarantees for all three major Ruby interpreters. And yeah, once what written, but how games this gem gives us options, what options it gives. So there are different collection classes that we can use, like arrays, hashes, sets, tuples, and different one map, which is like hash, but as the gem readme says, and also we in our tests saw that it's performed better than concurrent hash. It has its own methods for easier use. However, it's not 100% compatible with the hash operation, so you can't switch just from standard hash to this concurrent map. But it's very useful. Then there are values that are inspired by other languages, and even some additional classes for structure-like classes. So you can get immutable structure, where you can say that no thread can change it, or opposite, thread-safe change for mutable structures, or structure where you can set a value, but you can't change the value is set. And then there are quite a lot of classes for thread-safe variables. And we, in our regular work, use two of them. Atomic fixnum, which stores integer values, and you can interact, like increase, decrease value in a thread-safe manner. And if integer is not enough, then atomic reference, where you can store any object type and interact thread safely with it. So like, for example, store some time or float information. Okay, so we have now gem. Let's see how we could rewrite this threaded code, but using concurrent gem provided options. So first, we will use concurrent map instead of plain hashes. And there is still this assignment operation where we increase the value. So we will use atomic fixnum to fix it. And now we use this compute is if absent. So this will check whether the key is in the map. If the key is, it will return existing value. If not, initialize the value with the given block or given value. And at the end, we use increment method that will thread safely increment our integer value. So let's see how this executes. And most importantly, compare the numbers. We see the numbers are as expected, like almost 95,000, and also those previously that differed those counts, also those are correct. So nice, let's add those numbers in the table. And as we expected, in JRuby, it performed faster in threaded execution because we have true parallelism. They executed in multiple cores. Not so good with the JRuby because this overall overhead slowed things even more locking, more switching. So yeah, that's with this example, but I would add a few more things to it regards threading. So first of all, don't call thread new directly. In real applications, if you have multiple threads, it could be hard to detect which thread is responsible for what. You see only thread 1, thread 2, and etc. Or yeah, even threads without any identification. So what we are doing, and also would suggest others to do, is add the thread name just set to any you need information. So this case, this is like a worker pool thread that just executes some code parallel. But if you like spin up other threads, you can name them otherwise. And at the end, in the results in thread dumps, you can identify those threads and see, oh, the one that is stuck is responsible for this particular execution. So at least some point where to look. And additionally to it, better create encapsulation method for new thread creation. And in our case, having such a method helped us with the workaround for a JRuby bug. The bug was related to a new thread creation. So sometimes JRuby spinned up a new thread, but actually didn't spin up new Java thread. So therefore, we need to check whether there is actually a native Java thread, and if not, just retry one more time. If we wasn't this new thread method for us, then we will need to go to all our code to check where the thread new is called and think how to avoid error. And the second said like thread context. If you spin up different threads, add context information, for example, for logging or other critical information, so that the threads could log in the log file the same information as the main thread. Or maybe just add something new, but at least have this context. And second, global variable initialization inside threads, like global or instance variables. So I have here a small class and a method that will initialize an array. And then I spin up 10 threads and add value 1 to the array. And at the end, I return array size. So let's do a quick poll. How many of you think that the line on the right side will return 10? Maybe 9? So nobody for 9? 11? No? Okay, let's see. Okay, first time it returns 10, as expected. Let's try one more time. Still 10. Maybe third time we'll be lucky. Oh yeah, we got 9. So what happened here? Multiple threads at the same time initialized this array here. So the first thread initialized it, added this value to the array, and the second thread also initialized it, and result from the first thread got dumped somewhere in the strange array. And yeah, this is just a sample, but very important when getting new connection, like database connection or network connection. So here I have a method that creates a new network connection using Faraday gem. Then we create a new instance variable if it's not created, and we have close connection method. And if we look, a really bad day when thread 1 reads empty value, and then context switch occurs, and thread 2 reads as well empty value. And at the end, both those threads creates a new connection, but only this second connection is stored into this instance variable, and close connection call will close only the second connection. First connection will live somewhere up in the air, and like if there is network connections or database connections, more likely for database connections, at some point in production you don't understand why our used connection pool is going up, and database is complaining that it doesn't have any connection left. Or your customer complains you that, oh, why are you using all our database connections? So yeah, that could be the case, and actually this is case from our production, like not from our but customer production environments. And at the end, we added a code in specific places that it raises exception if we need to initialize a new database connection, but it's not a main thread. So that at least in our test suite, we could catch those cases if there is some flaky test that would like to create a new connection in a thread context, then it raises exception that no, you don't do this. And we catch like 5 more places where this was done. So yeah, it's very important. How we could fix this? One of the basic would be to already initialize this object with the connection, but there could be cases when we don't need connection all the times, and they would like to create connection only when it's needed. So then, there was this mutex synchronize thing, so we could use that one. So let's create a new mutex, call synchronize, and our connection is ready. Not so fast. Every thread should use the same mutex. Otherwise, each thread has its own mutex. It synchronizes it with himself. So no locking, and this will not work. Okay, so we create initialize new mutex and use synchronize. Yeah, it's quite straightforward. No, not so fast. This assignment operation still isn't atomic operation. There are 2 operations, so we need to protect it as well. So better solution, we can initialize the variable here in this synchronize block, but it's also not the best solution, because still we need to call synchronize each time we would like to access connection. So our approach is to add additional check. So you check that the whether value is initialized or not, and if it's not initialized, only then call synchronize and then create a new connection. And this maximum could create few synchronized calls when those threads actually do lock up. And but still, when they will go inside in the synchronized, they will see that already some thread initialized this connection, so we free to go. Just use existing value. So yeah, that's fixed for the second case, and let's do a wrap up of what we saw. So first of all, concurrency. It's not parallelism. So running multiple threads can improve performance, and actually in most cases it will improve, because most times you will need to wait on database or network, so you will get some performance boost. But if you have CPU intensive operations, the running on multiple cores will help speed up very much. Be careful when using variables in threads, especially instance variables or global variables, and to better reduce need to use them at all, but if needed, use gems like concurrent Ruby. For maintenance purposes and better debugging, don't use just thread new. Set thread name, set thread context, so that it's easier for you to use information inside thread, and also like for logging purposes. Initialize global and instance variables thread safely, so that you don't get ghost network or database connections. And this is the case where mutex synchronize is very valuable. And be sure that you use one mutex for your all threads, so that there are no mutex in thread context, so that they synchronize but only with themselves. And yeah, threads in JRuby are parallel, and can speed up code execution. In our case, it helps quite a lot because we have CPU-intensive operations, and speed off is very, very great. But keep in mind that interactions between threads and shared variables, that's something shady, and you can get flaky tests. And each time when we get a flaky test in our production, it's 99% that there is some thread safety issue that isn't thought out, and it's very hard to get those because you run on your local machine and it's running. It's no issues there, but it's running because maybe your computer is much faster than some GitHub Analytics spinned up virtual machine, and therefore you don't catch those. So yeah, and happy trading. So, yeah, thank you.